All right, so I'm recording this, and we are good to go. All right, so welcome to week 2. My plan is to continue talking about assembly language programming and about this business of file registers and destination bits, and looking at some examples of how we can do things with assembly language, but moving towards working on Lab 2, which will be dealing with input and output. So Lab 2, you're actually going to write code that'll do similar things to what we did in Lab 1, but you'll be creating the code yourself. So we need to talk about all of these things that were in the Lab 1 code that I said not to worry about for Lab 1. So let me start off by asking for homework questions or lab questions that people want to talk about. Actually, before we get to that, let me mention a few things that I said last week or over the weekend. One is that once class ends, and I'll say this again at the end of class, once the lecture part of class ends, I'm switching to my office Zoom, okay, and there's a link for that on Canvas. But that'll be structured like my regular office hours, so if you try to connect to me, it'll throw you into a waiting room if I'm talking with somebody else, and then as soon as I'm done with whoever was ahead of you, I'll bring you into the room and we can start screen sharing and so on. So if you try to connect between, say, 2 o'clock and 3:50, and it's not, it says waiting for the host to let you in, I'm there, okay, it just means that I'm talking with somebody else. But I'll be closing down the classroom Zoom once lecture is done and then switching to that one so that we can screen share and stuff in private. The other thing is general comments. So I talked last week about doing labs, and I said I want you to work on labs during lab time, and I want you to ask questions about lab during lab time or during lecture. And I discouraged you from asking questions about lab outside of those times, okay? The main reason for that is that to work on helping you with labs, we really need to sort of get into a Zoom session and do some screen sharing. Let me see what you're doing with MPLAB. Maybe I can do some things with it, and so on and so forth. That does not translate very well to email, okay? Especially, late night Monday before a lab is due and so on. So for labs, I really want you to try to take advantage of those in-class times, right? Both lecture and lab. Homework is a totally different story, okay? Homework, I'm very happy and available to help you with questions outside of class. Okay, you may not get an immediate response from me, but if you want help on homework, if you have questions about, what a question's asking or how to do something and so on, don't hesitate to email me, okay? The other thing is I opened up a Discord channel for the class. Chances are most of you already are familiar with Discord, already have accounts, but if not, there's an invite on Canvas. You can go ahead and accept that, set up a Discord account. It's a general chat area where you can post questions and talk to people and so on and so forth. I used this last year throughout the 200 level CS sequence, and it was pretty successful. I think people found it useful as a way to ask questions about, I don't understand what we're supposed to do for this thing, and somebody else would say, oh yeah, I same question, here's what I figured out, and so on. I'm not moderating it, so people are on their own to play nice and treat people well and so on and so forth. But it can be a useful resource. So sign up for that if you like, and feel free to post questions there. And if you tag my name in it, I'll get an email, and if nobody else answers a question, I'll hop in and respond usually after some time. So that's available also. All right, so with that preamble, questions on homework or labs or anything else? I'm going to open my window until it gets too hot. let's see. For problems, I'm at a weird angle now, I know. For problems 11 to 16, do we have to use literal operands because the problem states to use literals? Let me go back and see what these problems say. Alright, so literals and assembler directives use literals to add 9 to wreg. So yeah, I want you to use literals here because, for example, how can you add 9 to wreg? Well, you could say increment file register wreg 9 times. But that, you know, that works, but it's not a really efficient way to add 9 to a W register. Same thing with 14. 14, you could just say increment file register 40, but we already know how to do that, right? Question 1 asked you to increment file register 40. So yeah, I want you to use literals here as a chance to practice using literals and getting a better feeling for what they're all about.
Hey Nick.
Yeah.
So I was looking through the data sheet and looking at the operators
Okay.
that are listed there, and all of them like have a F, D, or A like displayed after them. Can you go over what those mean?
Absolutely.
Thank you.
So so I did post this data sheet quick summary guide, by the way, on Canvas. So this is just a 18-page subset of the data sheet, but it's got most of the pages we'll end up talking about, including this one. So table 20-1, right, your favorite table in the whole data sheet, shows a synopsis of all the instructions. So for example, clear F says clear a file register F. The things in uppercase on the left here, these are opcodes. Okay, these are saying what is the instruction that we're trying to do. We're trying to clear something, we're trying to complement something, we're trying to decrement something. The things after that, the F comma A or the F comma D comma A, those are the operands. Okay, and the main operand that we worry about is this one F. Okay, and usually for these byte-oriented instructions, the F is a file register. It's the address in memory of the thing that you want to do the opcode to. So if we're saying clear a file register, then F is, you know, what file register should we clear? Well, whatever one I specify after the word clear F. So if I say something like this, clear F 0x22, it means go into the memory, so this is the data memory, and go to location 22 hex, which is 34 decimal, right, and write 8 zeros into that location. In the notion of this table, right, this is F. And it corresponds to these 8 bits. If we were to code this thing into binary, that's what those 8 bits would be. The comma A, I'm still not ready to talk about. I'm going to hold off for a week or two on that. That's called the access bit. And I'm holding off on it for 2 reasons. One, it's really confusing. But 2, we don't have to worry about it for this particular processor because we have so little memory. The assembler inside MPLAB will take care of that bit for us. So for now, we're going to ignore that. But this bit D, we do want to worry about. So D is the destination bit. So if we're clearing a file register, right, we just specify the address of the file register. But what about increment file register? So incf f comma D. And we'll ignore the comma A, right? So if I say increment file register 0x22, that says read the contents of this location in memory, 0x22, and add 1 to it. Okay, the processor reads that contents, it gets this, it adds 1, and now it's got the number 1. Okay, it's going to write that back somewhere, but where is it going to write it? It's got 2 choices. It can write it back into memory, or it can write it into the W register. Okay, this D bit tells you where should I write the result of doing this opcode on this operand. So where do I write the incremented value of this memory location? So if this is a 0, you're asking it to write it into the W register. If it's a 1, you're asking to write it back into the file register.
And it can only be those two.
Say again?
It can only be those two.
Yeah, so the D is always a single bit. F is generally 8 bits. D is a single bit and A is a single bit. And the previous table breaks those out for you. So the byte-oriented instructions have an opcode, a D, an A, and an F. D is 0 for WReg, 1 to put the result back in the file register. And then F is the 8-bit file register address. It's different when you deal with literals. So when you look at the literal instructions, for example, add literal W, while they call it K, right? It's still just an 8-bit number, but they call it something different because this is not a file register. This is just a plain old number. If I say something like add literal W 0x22, has nothing to do with memory location 22. This is saying take the number hex 22, which looks like this in binary. Let's add that to the contents of W register. And let's take the sum and store it back into the W register. There's no destination bit with these. When you use these literal instructions, they're always going to go back into the W register. So you read a value from W, you add whatever this 8-bit number is that you specified here, and you store the result back in W. And so this table, right, can be used to understand the details of how these instructions work, what exactly they do. But that's the general sense. Byte-oriented instructions usually read a file register, modify it, and then either write the result back to the file register or to W. And the literal instructions usually read from W, modify using a literal value, just a bit pattern, and then write the result back into the W reg. And I'm probably going to run through some of these in MPLAB in a few minutes just to sort of hammer home the point. But does that help?
Yeah, thank you.
Okay, cool. And there's a general thing, I think we might have talked about it a little bit last week, but there's this idea of read, modify, write. This is one way that we can think of most instructions in a computer. Read something, modify it in some way, and then write a result back. And not everything does all of these. For example, if we say clear file register 22, there's nothing that has to be read, right? It's really just taking a 0 and writing it into file register 22. But most of our instructions we can think of as read something, modify it, and then write it back. And increment is a really good example. We say increment file register whatever, or add 1 to the W register, right? First we have to read something. So if we want to say add literal 1 to the W register, right? First the processor has to read the current value of the W register. What's W? Oh, it's equal to 7. Okay, then it has to modify it. Let's add 1 to 7. Oh, I've got an 8. And then it has to write that 8 back. Okay, I'll put an 8 into the W register. But it's 3 steps. And this is part of a larger cycle, which you'll see again and again, which is called fetch, decode, execute. And we're going to talk about this a little bit later today, but this is basically fetch an instruction from memory, like INCF 0x22, right? Or in reality, it fetches a bunch of 1s and 0s. So it fetches this bit pattern. And then decode it. Decide what this instruction is doing. This is like the homework question you're doing, where it says translate these binary instructions into assembly. So fetch the instruction, that means read these ones and zeros out of the program memory, and then decode them. Well, let's see, I've got a 0, 0, 1, 0, 1, 0. That's an increment instruction, and my D bit is a 0, so I'm going to write a result back to W, and my file register is this. Okay, I know what I'm supposed to do. That's the decode phase, and then execute. And this is what the CPU of pretty much any microprocessor does over and over and over again. Okay, as soon as you power it up, every time the clock ticks, there's a fetch, a decode, and an execute. And the execute is generally something like a read, modify, write. All right, other questions? I think your camera resolution might be low. I thought I just checked it. That's as high as it goes. It's an almost horizontal line. So at least when I'm looking at it, it's not looking terribly rasterized, but is anybody else seeing camera resolution problems? Because it could be my network connection too. Well, hopefully the video will come out reasonable quality, if not. Alright, and a few people are saying that they're getting good quality here, so interesting. Okay. The fun of Zoom and online. Oh, okay. All right, cool. Other questions? All right, and I'm not convinced the chat messages actually come to me, so it might take a few minutes. All right, questions on the lab. I haven't looked to see how many labs got turned in, but hopefully people were able to do the lab.
Quick moment. To the lab. So when I was doing it, I am still not 100% sure, like, what are the next steps that are happening, or what kind of information is getting stored or getting sent to a different location. Is there something I'm not really certain with just yet?
Okay. Well, that's a good segue, because I wanted to sort of jump into MPLAB and do some playing around with this for a few minutes, and see what we can tell by using the debugger. See what we can figure out. So this is what I call junk code. This was just code that we were playing around with. Let's make some changes to this. So let's move a 7 into the W register. And then let's add 1 to it. Let's copy that somewhere. Let's increment that. just some code to play with here. I'm going to load a 7 into W. I'm going to add 1 to it using an add literal. And then we're going to start moving things around. And I want to assemble this, right, build it, and start the debugger, and stop right here at the first instruction. And I'm going to look at my variables, and I still have variables in here from last time, including W register. Alright, so that doesn't really make it bigger. Actually, I'm really curious. Wow, that works. Okay. Alright, so you can put any variable location, any file register locations in here that you want. So 0x80, that's a file register location. That's a location in memory, right? And the current value is 0. WReg is actually another file register. It's actually in the same memory. It's got a different address. Its address is FE8. Okay, we'll talk about that later on. But it's a file register more or less just like any of these file registers. And most of these things are initialized to 0. That's not necessarily guaranteed. Okay, but the simulator puts these values at 0. When you actually power up a physical PIC processor, you don't know what the initial values are in most of these file registers. Alright, so if I step this one instruction, if I execute this move LW7, what is everything that's going to change in this picture? What's going to happen when I execute that first instruction?
Wouldn't it set a W register equal to 7 since we haven't taken any steps yet?
That's exactly what it'll do. It'll take the number 7 and it'll copy it into the W register, which means this value should change to a 7. So let me go ahead and do one step. And it makes it red to let me know that this value just changed. And now W is equal to a 7. Alright, now I'm going to do add LW1, which I gave you a comment here, which says set WReg equal to WReg plus 1. So that's a read, modify, write. This says read the contents of the W register. Right? We didn't specify that in here. You don't have to specify an operand. You don't have to specify a register with an add LW. Right? It's understood that this is going to work on the W register. So it's going to add the literal 1 in this case to WReg. So this should read WReg, which is a 7, add 1 to it, which is 8, and then write it back into the WReg. So if we step that, WReg changes to an 8. And it's color-coded red again because it just changed value. Alright, so what happens when I say move WF num1? What's going to happen there?
Would the location of 0x80 change to 8?
Exactly. So this says take the contents of the W register, which is 8, and copy that into file register num1. Well, num1 just means hex 80. So copy the contents of the W register into file register 0x80. Right? That's a location in memory, and that's the value that we're looking at right here. Right, at location hex 80, right now we've got a 0 in there. When I execute this instruction, that 8 from WReg will get copied into here. This variable right here should change to an 8. So step that once, there's your 8. Alright, so that was a read, modify, write. The read was read the W register. Modify, well, it didn't do anything, right? It added 0 to it maybe. And then write, and the write was write it into file register 80. Okay, now our next instruction, increment file register num1. So what is that going to do? This one's trickier.
What does increment do? Just a hint.
So increment, I'll give you better than a hint. INCF increment file. Increment means add 1. but you can go to the full data sheet, and if you go down to chapter 20, all these instructions are actually spelled out. So here's increment F, and the operation is take the contents of file register F, add 1, and send that to whatever the destination is. So increment is adding 1. So we know it's going to read the contents of num1, which is an 8. It's going to add 1, which will give us 9. What's the destination? Where is that 9 going to get written?
Would it still stay at location 8?
Yep. So since we didn't say comma 0, the destination is the file register. So this says read the contents of num1, modify it by adding 1, and then write it back into num1. So after this instruction...
To interrupt, if we did have a comma 0, would it be written to the wreg?
Exactly, which we're going to do in 2 instructions just to
so
see.
By default, it's going to be at 80.
By default, it goes back to the file register, which in this case is
Right,
80.
okay.
Yep, you got it. Alright, so we'll increment this, and now file register 80 has the value 9. We're going to do that a second time, and it should do exactly the same thing, except when it reads it, it'll see a 9. When it adds 1, it'll become a 10, and it'll write that back. And remember, we're in hex, so this is 0x0a. That's how we write 10 in hexadecimal. And now we're going to increment that one more time. So we're going to read from num1, which is a 10. We're going to modify it by adding 1, which will give us 11, which is hex B. But then we're going to write it, because of this comma 0, we're going to write it into the W register. So 0x80 has the value 10 decimal in it. The W register has a value of 8. So when we say increment file register, I'll just say 0x80 instead of num1. But with a comma 0, it's saying read the contents of this memory location, which is 0x0a. Increment, that's the modify, which is 0x0b. And then the write part, this bit right here, says write it into the W register. So W reg will change to hex B, or 11. And this will not change. Okay, we never said modify the contents of the file register. We read the file register, we updated it in our mind, but then we wrote the result into the W reg. So 80 should stay unchanged, and the W reg should get the value of 80 plus 1, which will be B. So when I execute this instruction, this should stay A, and W reg should change to B. Right, so there you go. Alright, what about move F num1? This is a weird instruction.
Will it not do anything?
It basically doesn't do anything. It reads the contents of num1, which is file register 80, so it reads this hex A. A move F doesn't do any modification, so it's still got a value of hex A. And then it writes it back somewhere. Well, since we didn't say comma 0, it writes it back into the file register. So it basically reads this value from location 80, and then it writes it back into location 80. It's kind of what we call a no-op, something that doesn't actually seem to do anything. Right, so the operation of a move F is just read the contents of the file register and copy it to the destination. And if the destination is set to the file register, it just copies the file register to itself. So after we do this, we should see no change. Right, the file register was A before, it's A again. as compared to this instruction where we say move f num1 comma 0. Now here the comma 0, that says the destination is the W register. So it's going to read from location 80, which is an A. It's going to write it into the W register. So our W reg should change to an A at this point. And yes, that is the default. So if we don't specify comma 0, it goes back into the file register. It treats it as a comma 1. So default is going to the file register. If we wanted to go to the W reg, we have to say comma 0. So if we execute this instruction, it read location 80 was an A, and it wrote that into the W reg. And then the move FF says copy from file register num1 into file register num2. Okay, it's another read, modify, write where there's no modify taking place. But it's a peculiar instruction because it's the only instruction that lets us move from a file register to a file register. And it lets us do that because the instruction actually takes 2 instruction words to specify, and it takes twice as long to execute. So when you code this in binary, we specify 1 file register, and we specify the destination file register. And there's no destination bit, there's no access bit, it's just 2 file registers. And it moves from one to the other. It's a really powerful instruction. If we didn't have this, we'd have to say something like move num1 into W, and then copy the W reg into num2. And that works just as well, and it's just as fast, but it changes the value of the W reg. And if we don't want to change the value of W, move FF can be useful. So this should read from num1, that's location 80, not do any modify, and then write it back into file register num2, which is 82. This value right here should change to whatever the value of num1 is, which is hex A. So we execute that, there's our hex A.
Quick question.
Mm-hmm.
So, about the breakpoint,
Mm-hmm.
Is it always needed, or is it just something we would see happen like step by step?
So if you don't have a breakpoint set, right? Let's go ahead and rebuild this, and let's go ahead and start debugging. My program is just running, right? The simulator is going through all of the instructions in order and executing them, but I can't, single step it, right? It's running. You can tell from this little bar down here. So I can pause it, right, and then try to single step it. But I've run a bunch of code already, and I don't know what it might have done. So usually, if you want to start stepping through one instruction at a time from the beginning, you put a breakpoint in the beginning. If I didn't care what was happening until I got down here, I could put my breakpoint here, right, down at the end. And now if I say go ahead and run, it will really quickly run through all of these instructions, and it'll stop when it gets here. And if I look at my variables, I can see that all this stuff has been set up just like it was before. So typically when you're debugging code, you'll have a bunch of stuff in the beginning that you may not be very interested in. It may be stuff that you already know how to do, you've taken it from other code or whatever, and it may be, somewhere further in the program is this unique part of code that you've written that has something going wrong. So you'd set a breakpoint in the beginning of that and then start stepping through one instruction at a time.
I see. So it's like just a way of checking yourself.
Yeah. And if your computer science track, right, when we get into CSE 224, this is something that we'll do a lot of. You write a program and you run it, and if it works, great. But if it doesn't work, what do? Well, you can use a debugger. And there's debugging tools that look similar to this that let you basically step your program one instruction at a time, look at the values of variables, maybe change the values of variables, and see what the computer is actually doing versus what you thought it was doing. And it's a way to find out where the disconnect is between what you told the computer and what you wanted to tell the computer. So that's a whole nother subject in CSE 224. That's actually a big part of that course, is just debugging.
Hi, I have a quick question about the debugger.
Sure.
So when you have that variable watch list, you have like name, value, type, address. Is there any way to add like notes to them, like with like text saying 80 is num1?
Yeah. It feels like there used to be a way to do that, and I don't believe there is. So I mean, it would be nice if you could just do this, right? But it doesn't like that. Yeah, I don't know a good fix for that. And it would be pretty easy for them to just let you supply another field here. But I don't think there is. Get a post-it note. Just pop it on your screen.
Okay.
That's a bit of a general debugger thing also. If you're debugging something like written in C and you know that you're going to debug it, you can specify options when you compile your code so that you can look at things with their name. So I could look at a variable called answer, right? But if you don't have access to that, you know, sometimes you have to know that answer is stored at location hex 7FFF4826, and you just have to keep typing that in again and again and again, and it's kind of a pain, but that does happen.
Okay.
Alright, so let me go back to the beginning of this. Let me put my breakpoint in the beginning. And let's look at a few other things while we're doing this. So up here at the top of my screen, there's a box that says PC. This may look different on yours. These things can be moved around and customized. But somewhere up at the top, there's probably a box that says PC : and it says 0x10. And then there's this other box, and it has a lowercase n, o, v, z, d, c, c. It's like an eye exam, right? Colon, w, colon, 0xa, colon, bank 0. Let's see what happens when I start debugging this. So let me just go ahead and start debugging. And my PC changed to 0, and my W and my N, O, V, Z, D, C, all of those are the same. This PC, this is the program counter. Okay? Program counter is the thing that says what instruction am I about to execute in memory. So we've talked about the data memory a fair amount. There's a second memory which is called the instruction memory. And what do we find in the instruction memory? We find the ones and zeros that say, what do I want this computer to do? What's my program? Okay, so this is 16 bits wide. And if you were to actually look at the instruction memory, what you'd see is your assembled code. So here's the contents of instruction memory. Here's the address on the left, 0, 2, 4, 6, 8, 10, 12, 14, and so on. And here's the ones and zeros stored in those locations. And these are the ones and zeros corresponding to each of these instructions that we've written. So take those instructions and code them up, you know, using these bit patterns. Right, like this. And that's what gets stored inside the program memory, or the instruction memory. And that memory is addressed by something called the program counter. Which is usually just called PC. And the PC is used to address the instruction memory, to ask for the contents of some location in instruction memory. So what do we start with? Well, when you power on a PIC processor, when you start the simulator, the PC is always equal to 0. Which says the first instruction that's going to be executed is whatever is stored at location 0 in that memory. And if we look at our disassembly listing, we can see that's the instruction move LW7. So this instruction is the first one that's going to be executed. Well, we figured that out already. But this PC:0 kind of confirms that for us. All right, let's go ahead and execute that one instruction. I'll put my variables back. Let's execute that one instruction, and the W register changed to 7. But if you look up here, the PC is now equal to 2. Okay, that's the address of the next instruction. And again, yeah.
So since we know how to like set W register to 0, would we always have to use move LW to set something such as like the W register, or could we use some kind of other operand?
If you want to put a particular value into a register, you're probably going to use move LW. But there are a few exceptions. For example, if you want to set a value to 0, you can say clear F. If you want to set a value to all 1s, you can say set F.
Alright.
But usually we just use move LW. Even if we want to load a 2 into a register, it's faster and takes fewer instructions to say move LW2 than to do a couple of increments. All right. Let me add something else in here. Add some new code in here to play with. So I'm going to clear file register num3, which is x84. I'm going to increment it once, I'm going to decrement it twice. And let's see what happens when we do this. If you have a disassembly listing open, it seems like every time you build your project, it'll switch to that view. So if that bothers you, you can just close this out. Alright, I'm going to put a breakpoint right here because I'm not too interested in these earlier instructions yet. So let's go ahead and run this. And so it says debugger halted down here. Debugger halted. And it tells me breakpoint hit at line 13, okay, which is where the green line is, so it always shows a green highlight for whatever instruction I'm about to execute. And over here it tells me my PC is 0xa. Okay, I shouldn't have closed out that window. Let's go back to the disassembly listing. So instruction A, that's my clear F 0x84. That's my clear F num3, that's this instruction right here. The PC colon 0xa tells me that that's the 10th instruction in memory. What's actually the 5th, because instructions take 2 locations. But it's the instruction stored at location 0xa, right, 10 decimal. And it's the instruction about to be executed. So PC always looks ahead. PC is saying, what's the next instruction to run? So I haven't done my clear F yet. Okay, and the W register is 8 because of other stuff we've done. But I want to look at some of these other things up here, this NOVZ DCC. Okay? And they're labeled status flags. And I'm going to go ahead and I'm going to add one more watch down here. which I'm going to call status. And status is a built-in register. It's stored at location FD8, and its value is 0. Okay, I'm going to execute one instruction. I'm going to say clear file register num3, and a bunch of things are going to happen. All right, I clear file register num3. Well, num3, right, which is at 84, that was already a 0, so we didn't see anything happen there. But this status register changed to the value 4. Okay, what does that mean? So let me see where I put this in here. Put it at the bottom. Alright, this is probably your second favorite table in the data sheet. And it's not alphabetized, but I'm looking for the word status.
There it is. Lower down.
Status. Thank you. Alright, so status right here. Status, you know, it's an 8-bit register. It's a file register, so it's 8 bits. These upper 3 bits are unused, but these lower 5 bits are labeled N, O, V, Z, D, C, and C. Well, those are the same as what we had up here in our eye chart, N, O, V, Z, D, C, C. But notice the letter Z is uppercase now. Okay, this is a shorthand. All right, so what are these status bits? To do general purpose programming, you need 3 things. You need a way to do you need a way to do sequential statements, increment a file register, move a file register, that kind of stuff. You need a way to loop. Okay, branches and go-tos, and we'll talk about those, but those are pretty easy. Those are basically saying, after you've done a series of instructions, go back and repeat those instructions. Or go somewhere else and read some instructions. But you also need a way to do ifs, to do conditionals, to test for some condition and then change what you do based on the status of that condition. Okay, on a PIC processor and a lot of other processors, this is done by using what are called status bits. And these status bits, it's just 5 bits, are updated based on what the processor is doing. For example, it just cleared a file register, num3. That means it set num3 equal to 0. Well, any time that the CPU does something that results in a value of 0, it makes a note of that. And it makes a note by setting a particular bit inside the status register. In particular, this 3rd bit right here, labeled Z. So anytime you find that bit is a 1, it means the CPU just did something that resulted in a 0. So let me make a table here, and I'll show you this in a second. So this is N, O, V, Z, D, C, and C. So this is what the status register looks like. And we looked at this before, and it was all zeros. Well, when we're looking at it now, the status register is equal to hex 4. Hex 4 looks like this. Right? This is the pattern for 0, this is the pattern for 4. So if we look at the status register and we see a value of 4, that tells us this Z bit has been turned on. It's now a 1. Let me see, we got a chat question. Is there a way to lock Windows tabs in the IDE? I don't know. That's a good question because they move around a lot. And I feel like I've bumped across something somewhere that let me lock those, but maybe that was Eclipse. So I don't know. Alright, so our status register changed to a 4. That means this bit labeled Z is a 1. That's also reflected by the fact that this Z up here has become uppercase. So you can use these status bits to help you see what has happened in the processor's mind, basically. And Z is probably the bit that we're going to be most concerned with. Because if you can tell if something is 0 or non-zero, you can do most of what you have to do. But there's another bit, N, which lets us know if something is negative. There's an OV bit, which lets us know if an overflow occurred. So if we try to add two numbers and the result is too big to fit into 8 bits, like we want to add 200 and 150, that answer is too big to fit in 8 bits, the overflow bit will tell us that. And then C is a carry, which tells us that we're getting a 1 coming out of the most significant bit. And DC we'll talk about another time, but that's a decimal carry. That's a carry out of the 4th bit. And there's reasons why we want that. Mostly we're going to work with Z, and probably second most we'll work with the negative bit. Alright, so we just cleared num3. The 0 bit got turned on to a 1. Oh yeah, I'm going to increment num3. Let's execute that 1 instruction. What happened? Well, num3 got changed to a 1. The status register changed back to a 0. Why? Because the 0 bit just got turned off. Why? Because the result of the CPU's last instruction was not 0. And so again, up here, the Z bit is lowercase. That tells us that we did not have a 0. Now we're going to decrement num3. That's going to...
Isn't that just the opposite of increment F instead of +1 is -1?
Yep, that's going to do exactly the same thing as increment F, except it subtracts 1. So num3 is currently equal to 1. When I decrement it, it's going to change and it's going to be equal to 0. But when that happens, the CPU is going to say, hey, I just generated a result that's equal to 0. It's going to turn on that 0 bit. And this Z will go uppercase, and the status register should go back to 4. So the 0 bit is set, but it also set this decimal carry and this carry bit. So it actually changed both of these to be a 1 also. And we're not going to worry about why that is for now. But decrementing is subtraction, which means we're adding a 2's complement, which is going to get into carry bits. But the part that we're interested in is that 0 bit, right, the 3rd bit of that status register definitely got turned on high. And we can see that with the Z being uppercased. Now if I decrement once more, what's the new value of num3 going to be? What happens when I decrement 0?
Wouldn't, instead of having, not just hypothetically speaking, it would be 1x0, 0? Or 1x01? I'm not sure, just guessing.
Okay, reasonable guesses. So first of all, this 0x is always just 0x. That's just a code to tell us this is hexadecimal. So those can never change, but these 2 characters that we see here, those can definitely change. So you and I, what do we get when we take 0 and subtract 1? What do we call that resulting answer?
A negative?
Yeah, it's just -1, right? Okay, so who knows what -1 looks like in binary? Or what that even means?
Wouldn't it just be 1, 0, 0x1, 0? Well,
0x10, if we write that out in binary, it looks like this. Everyone agree with that? And if we remember 2's complement, this tells us that this is a negative number. So to find what it's the negative of, what do? We complement everything, and we add 1. And we get this, which is the number 128. So this would actually be negative 128. It's that weird extra number at the bottom of the table when you write out things in 2's complement. It's like negative 8 when we do 4-bit 2's complement. So that's a really, really negative number. So how can we find the bit pattern to write a negative 1 in 2's complement? What procedure can we follow? This is engineering 250 stuff.
Take 1 and complement it.
Cool. Let's start off with the number 1. And I'm going to write it as an 8-bit number. I'm going to complement every bit. And then what's the last step?
Add 1.
Add 1, good. So 2's complement, if you want to find the negative of a number, complement all the bits and then add 1. So start off with a number positive 1, take the complement, add 1. That gives you the 2's complement notation for negative 1. So what would I get if I wrote this in hex? What would it look like?
0x11. 1.
Close. 1 would be 0001. This is actually FF. So we have to use this idea that if we want to write the digits 0 through 9 in hex, it's just the binary representation of 0 through 9. But we have these other bit patterns that we don't have single digits that correspond to them. And so we use letters. And those you just have to memorize. You get used to them after a while. But you just use this as a stand-in for that pattern. So 1111, that's the most common bit pattern you'll encounter other than 0000. And that's just an F. So put all that together. I'm about to decrement num3. I would expect num3 to change from 00 to FF. So let's go ahead and do that, and sure enough, that's the new value, is FF. My status register is now hex 10. So what is hex 10? Well, there's my 0001, that's the first hex digit. And then 0000, that's my other hex digit. So my status bits should look like this. Every bit should be off except for the N bit should be a 1. And that's exactly what's happened up here. My letter N is uppercased. Everything else is lowercase. So my status register is telling me whatever the CPU just did resulted in a negative number. Which it did, right? It resulted in a value of negative 1. So the status register is telling us information about what just happened. And that's going to be useful when we want to do things like, say, keep subtracting 1 from this register until it's negative, or until it's 0. And then at that point, let's do something else. So for example, in C, you might do something like, x equals 10. While x is not equal to 0, do something. X equals x minus 1. End of loop. So we want to initialize, this is just plain old C pseudocode, initialize this variable x to 10. If it's not 0, do something, and then change x to 9. It's not 0, do something, change x to 8. Keep doing this until x is 1, do something, now change x to 0, and let's leave our loop. So this is a move LW instruction followed by a move WF. And here we want to do something to test whether or not x is 0. Well, what could we do? Well, we could add 0 to it, right? Or, you know, when we do our subtract 1 from x down here, we can check the 0 bit to see if x is 0. And we'll have instructions that'll say, for example, if that 0 bit is not set, then jump back up here and repeat these instructions. So these status bits will be used a lot, and they'll help us do conditionals and things like that. Alright, let's see, questions. If you decremented FF, would it go to -2 or 254? Yes and yes. So let's do that. Let's just add another decrement in here. Sometimes I can move this window out of the way, and sometimes it breaks everything. Let's see what that does. I don't know if that's better or worse. So let's go back here. Let's put our same breakpoint. Let's start our debugger. Let's look at our variables. And let's step through to where we were. So we started off with num3 is 0. Then we incremented it to a 1. We decremented it to a 0. And then we decremented it to an FF. That's -1. If we do another decrement, it should subtract 1 from -1 should give us -2. And -2 looks like this. That's +2. Toggle all the bits, add 1. That should be -2. This is F followed by, that's the binary pattern that we call E. So this decrement should change file register 84 from FF to FE. Alright, so there you go. Yeah, this bugs me. I'll put it up there. And if you right click on this column over here, I can click this box that says decimal formatted value, and I'll get a new column which will show me the value in decimal. Usually there's a way to ask it to do signed. I don't think this debugger will do it. But other debuggers, usually you can say, show this to me as just an unsigned number, or show it to me as a 2's complement number. So why is it 254? Well, this is, you know, 254 in decimal, right? 8 ones would be 255, that's 1 less than 256, but if we just add up powers of 2, that's the number 254. So the debugger is not showing us 2's complement value, but if it was, then it would also show us this was equal to -2. Let me see, questions. Let's see, question, is it good general practice clear all the address registers we are going to use in our code at the beginning? Probably not. So the question is, should we clear file registers in the beginning? Only if you need to, right? For example, here I'm going to take a 7, add 1 to it, and put that into num1. There was no reason I needed to initialize num1 to any particular value, because I'm giving it a value here before I start using it. But this is like, you know, writing variables in C. If I'm saying x equals 10, right, there's no reason that I would say, you know, something like x equals 0 in the beginning, even though people do that. That's just redundant. But the reality is, if you don't do this, right, your variable will have some effectively random value before you start before you initialize it. And maybe that's okay, or maybe that's a problem. So it really depends what your code is trying to do. All right, so on the business of these status bits, I've told you to reflect what the CPU did. Well, that's not entirely 100% accurate. In most cases, the status bits tell you what the CPU just did. But it really depends on what the last instruction was that was executed. For example, if I say add the W register to a file register, all 5 status bits are updated. So if the result of adding W in a file register is 0, my 0 bit will be asserted. If the result was negative, the negative bit will be asserted. The move F instruction only sets the 0 bit and the negative bit. The move FF instruction doesn't affect any bits. So if I say move FF num1, num2, and num1 happen to be 0, does not make any difference. The 0 bit is not going to be changed. So when we get to the point where we're worried about setting status bits, we need to come back to this table and make sure that whatever instruction we're hoping to monitor is actually affecting the status bits that we're planning to test. So that's what this column is in that table. All right, let me look at more chat questions. It'd be really nice if my phone was smart enough to stick to landscape mode so I don't have to tilt my head to read these. But that's why I'm tilting my head. Or I'm just going to tilt the phone. So don't get dizzy. So we know that the...
If you have an iPhone, you can lock the screen.
Yeah, I don't have an iPhone.
They could, some kind of option, pretty sure there should be.
Yeah, hey, that was easy. All right, thanks. All right, so let's see, questions. So we know the value is representing -2, but the debugger says 254. If we were to use something such as printf to get the answer, how does MPLAB know whether to show -2 or 254? So that's an interesting question. When you say printf in C, you could be printing as an integer or as an unsigned integer, and you could have the same bit pattern, and sometimes you'll get a 254, sometimes you'll get a 2 or a -2, right? If it's a 16-bit integer, a -1 looks different from a 32-bit integer -1. If I have -1 as a 16-bit number and I print it as a 32-bit number, I'll get a positive number, right? I'll get 65,535. So it's part of what we do in C is we specify types of variables, and we can say unsigned int or short int or long int and so on. And those are used to change the code that's generated at the assembly language level. I don't know what MPLAB would do if you wrote C code and did a printf. It would depend, I think, how you declared the variable. So another question, would we ever have to clear a variable before exiting for security reasons? Yeah, and that's another really interesting area. If you are on a shared system and you read a password in or a social security number or something like that from a user and you copy it into memory, what happens when your program exits? It's possible those values are still sitting in memory. Even if they're in a local variable, and actually especially if they're in a local variable, the memory on a machine is shared among multiple processes. And once your process exits, that memory is theoretically available to other processes to use. And that social security number or password that was typed in and you did some processing on and left in a local variable could be the initial value of a variable for some other program that's running. And if I had a program that just said, show me the value of these locations in memory, it might have, information in there that's sensitive. So, good architectures will do things, will do housekeeping when a process leaves an execution context to clear those things up. There'll be memory separation models and things like that. But yeah, those are good concerns and good things to keep in mind, that this stuff is all just ones and zeros, and the fact that it's a password or a piece of sensitive information makes no difference to the CPU, right? It's still just ones and zeros, and this is something important to keep in mind. If you use a password manager that stores all of your passwords, and you go in and you look at your passwords and so on and so forth, what happens to those plain text passwords that you were looking at? What happens to the locations in memory that those were being read from? So you want to make sure that your manager is taking care of that. If you use an open source manager, you can look at the code yourself and figure out how that's handled. All right, let's see. Yeah, you're welcome. All right, so let's do a 5-minute break, and we'll come back, and I want to talk about doing input and output, and that'll take us into lab 2. So let's stop for about 5 minutes, and I'll come back and we'll continue with this.